Hey there, it's Professor Bennett from digitalaudiotheory.com. This programming example, 6.3.1, comes from Chapter 6, which covers dither. All digital audio, whether derived from analog capture or undergoing word length reduction, experiences some amount of signal truncation. Can't be avoided. Recall from Chapter 5, a reduction of bit depth introduces some artifacts that impact the sonic fidelity. First, the quantization process increases the noise floor. And secondly, a specific type of distortion is created in which the noise floor modulates with the signal. This is a perceptible distortion, especially for low amplitude signals. But fortunately, noise modulation can be mitigated through the use of dither. A dither signal is simply some very low amplitude noise that can be broadband or frequency specific, which is added to the audio signal prior to quantization or word length reduction. And while many types of dither exist, the goal of each is the faithful representation of the source material with only negligible artifacts arising through the quantization process. Now, at first blush, it may seem counterintuitive to add noise to the audio signal. This appears to violate our principle of transparently representing the audio signal. However, it was discovered that the audibility of adding some very low-level noise was much lower compared to the audibility of the distortions related to quantization, such as noise modulation. Now, one approach to removing noise modulation is to add a very small amount of additive white noise known as dither, in this case RPDF dither, for rectangular probability density function dither. Now, RPDF dither is randomly generated and has an amplitude of half a quantization level, Q over 2. Dither allows a quantized signal to break out of the quantization level that it's currently stuck at. Since dither is randomly distributed, then even small changes in the underlying signal are enough to bias the dithered signal towards the next quantization level. But dither comes at a cost. Since RPDF dither has an amplitude of Q over 2, we can think of this as a signal that occupies half a bit, thereby raising the noise floor by about 3 dB. In this programming example, we will create dither and apply it to a quantized signal. Then we can observe the impact on the quantization error and noise floor. So we're going to generate 50 milliseconds of here's duration's 50 milliseconds of a 40 hertz cosine with a sample rate of 40 kilohertz. This is going to be amplitude of 1, so -1 to +1, with a bit depth of n equals 8. And we're going to use the same quant bits function that was developed in Chapter 5. So here's going to be our signal. Let's go ahead and build this. So we're taking 2 times pi times our frequency times our sample vector divided by, or sample index vector I should say, divided by our sample rate. Then we're going to pass that through a quantizer to generate x8. Let's plot this. There we go. Next, we're going to generate dither to add to the quantized signal prior to quantization. The dither will derive from a pseudo-random noise generator within the range of plus or minus 0.5, which we're then going to scale by Q, making it within the range of plus or minus Q over 2. The dither will be added prior to quantizing, and we can compare the different 8-bit versions with and without dither. So here's our Q. We're going to use that to scale our dither, D. Here is the random noise signal that is the same 50 milliseconds in duration. This is going to give us a value between 0 and 1. So if we subtract 0.5, now we're between minus 0.5 and positive 0.5. If we scale by Q, we're between minus Q over 2 and positive Q over 2. So we're going to take that dither and we're going to add it to our original signal prior to quantization. We're going to plot that. Now let's take a look at what happens here. It's more noticeable up here at these extreme ends. Here we go. So blue is the unquantized signal, and you can see that it follows this stepwise progression up. It stays at a quantization level until it's ready to come back down. And we get the same stepwise progression down. If we zoom in even further, though, we can see the dither signal jumps between quantization levels, creating a fuzzier edge. Now, in theory, we say that a signal of Q/2 amplitude, which occupies half a bit, should be adding about 3 dB to our noise floor. We can see how much noise was actually added. So first we're going to take the RMS value of our dithered signal minus our original signal. So this gives us our total error, including quantization error and dither. And we're going to compare it against the RMS of just our 8-bit undithered quantized signal against the original. So this includes the dither plus quantization, and this includes only quantization. So we're going to see the impact of just the dither by comparing these two actual signals. We should get something in the ballpark of 3. 2.9, pretty close. So dither increases the noise floor by a predictable amount, and this prediction matches closely with the amount of noise actually added. Furthermore, it can be shown that the PDF of the dither is indeed rectangular using the histogram function. Here we're going to set 50 equally spaced bins between minus Q/2 and plus Q/2. And if the RPDF dither doesn't look rectangular, what we can do is we can try increasing the length and rerunning. We saw this in a previous programming example. We had to get about 10 million data points before the PDF truly started to look like an actual rectangle. So let's see what we get here with a lot less than that. So I'm going to clear the figure out. So we're going to pass in the dither. We're going to set the edges. We're going to set the bins starting from minus Q/2 to plus Q/2. We're going to set 50 bins for the histogram, and we're going to set the normalization to PDF. For octave, it's going to look a little bit different. We don't have these PDF options, and you're going to use hist instead of histogram. So there we go. Doesn't look like a perfect rectangle, but it's rectangular-ish. Let's take a look at this too. So let's create this time vector, and let's create a very small signal x. Look at this. So x is going to be, here's a cosine, 40 hertz, and if we set it to q, then it's going to occupy, it's going to have an amplitude of 1 quantization level. But if we then divide by 4, what have we done? If we then divide by 4, we've created a signal that is less than 1 quantization level. It's not going to be capturable by the 8-bit encoder. However, once we add some rectangular dither to it, let's clear that figure out. We'll see what happens when we add the dither. So here's our original signal. We could also plot the quantized version, which we actually don't have yet. Let me make a quantized version just so you can see it. So we're going to plot it without the dither. 0, right? It's too low. The signal's lower than a Q level, lower than it can be captured by the quantizer. But now, if we add some dither to it, so here we have X8D. So that's quantized, but with the dither added. Now when we plot that one, what do we see? We do see this noise modulation still tracking with the phase of this very low level signal. So while we have gotten rid of some of the noise modulation, at very, very low level signals, some noise modulation still does exist. Now this is an extreme example, but it's just to prove a point. So in the next chapter, we're going to look at, or in the next programming example, we're going to look at another type of dither that adds even more noise, but is even less perceptually noticeable. Thanks for watching.